Yes, right now.
Yes,
It's mute.
Okay.
For this presentation, we are 4 people, once per chapter, more or less, and is
Okay.
introducing all of this. I need to next slide, or I give the control.
Yeah, so I'm giving you control. I'm giving control to. Okay. Yes. I think I made you presenter. I'm not too sure what that means, but I think it works. And my apologies.
No,
You have to keep the lead, and if you want to share your the presentation.
Okay, do you stop sharing? Do you stop sharing? Did it? I think I clicked the wrong option.
Marcos the control, yeah.
Okay.
No, only control at the end.
Yeah, I made a mistake there. Change presenter.
At the end.
Can I go back to me? Yeah, show my screen.
Okay.
Sorry, Marcos.
No.
I had a blank moment. Can you see my screen again?
Yes.
Okay, good. No, Marcos. Yeah, I have a little thing again. I have. Perfect. Yeah, that should work.
To go forward, I need to push.
I think you should.
Yeah, if you click on your mouth, if you click left or.
What
are you looking for?
Yes, I don't. I try to go.
Yeah, there you go.
Okay. Thank you so much.
No problem. There's a bit of a delay, so don't press it 3 times because it will go three slides up, but slowly. No.
Okay. Thank you. Okay. Good morning, everyone. My name is Marcos Morandeira, and following slides, we will explore the digital tools for efficiency, biomaterials design, and manufacturing, developed by SIMCON and AIMEN. No, I try to go forward, but.
Okay, I can take the lead if you want and just move the slide. Just ask me.
Okay.
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 No,
next slide, please. Okay. Today's session is structured into 5 key chapters. First, we will explore the digital platform overview. Then we'll dive into the concept of the hybrid digital twin. Continue with the decision support system for product design. Next, decision support system for manufacturing. And finally, we will conclude with a live demonstration of the digital thread. Next slide. To start our technical journey, we need to understand the infrastructure that makes everything possible, the digital platform. And to give us more details, please welcome our first speaker, Christian Vega from AIMEN. The floor is yours, Christian. Sorry, the screen is Nicolas, the chat.
Yeah, and
it's your chat, I think.
Yeah, and you switch.
Yeah. I don't know what happened there. Sorry.
No. No worries about.
Yeah, it's like the presentation went off for some reason. Let me just restart it there. Sorry. How do I do that easy? Slideshow from current slide. Okay.
No, it's good.
It's good. Yeah.
Sorry. The next slide, please.
Yeah. There.
Thank you so much.
We cannot hear you, Christian.
Christian, you're mute.
No, we have the same problem than Isabel. We cannot hear you. Are you in the same room with Marcos?
No.
No, no, no.
No, it's good. Yeah, try.
Yeah, now?
Yeah,
Now
yeah.
it's perfect.
Okay. Good day, everyone. My name is Christian Vega. Regarding the digital platform, if you can go further, a slide, please.
That's
okay. The core mission is to optimize manufacturing processes by ensuring product quality, process interoperability, and seamless flow of information across the entire value chain. This platform is designed as an end-to-end digital system that supports the production of flexible, high-performance bio-based products, targeting industries such as construction, medical, and packaging. From an architectural perspective, the platform is fully containerized and based on microservices approach using Docker, which makes the system modular, scalable, and easy to deploy. As you can see, the architecture is organized into clearly defined zones. So zone 1 focuses on access security. We're using, can you go one slide back, please? Yeah, okay. So zone 1 is using Keycloak, both through proxy and traffic services to manage authentication, authorization, and secure access to services. Zone 2 handles storage and events, where MinIO provides distributed and scalable object storage, and event-driven mechanisms enable efficient file handling and data integrity. Zone 3 contains the management logic, including File Manager API and databases such as Postgres and Mongo. And finally, Zone 4 is dedicated to IoT and data motion using technologies like MQTT, Telegraph, and InfluxDB. So overall, this architecture is designed to be scalable, secure, and interoperable. Okay, that's it for my side.
okay. Then, with the infrastructure in place, we now moved into chapters 2 and 3. Grégoire Audoit, on behalf of SIMCON, will guide us through hybrid digital twins, explaining how their integration enables production optimization, and then take us further into the decision support system for product design, showing how AI-driven models are applied to achieve better product. That's your floors.
Thank you, Marcos. Hello, everyone. So I'm Grégoire Audoit from SIMCON in France. I'm head of R&D here, and we basically, our core work generally is developing and selling rheological softwares for injection molding. And here I would speak more about the work we have on the digitalization in Bio-Uptake, and I will start with the hybrid twins. Please, next slide. So what is a digital twin? We could simplify by saying that it is a modelization. It can be a process, a product, and an infrastructure. Basically, we have an input that we put in a manufacturing process, and we have results. And the digital twin tries to modelize what happens as a black box in the manufacturing process and give us the same results. So in order to have predictable results, these digital twins can be statistical, it can be physical simulations, it can be deep learning or machine learning, and it's useful for maintenance prediction, process optimization, and traceability. Next slide, please. Why are we speaking of hybrid twins in this case? It's because we created the model from real-world data and from simulated data from finished element analysis, so rheological simulations. For the simulations, we needed characterization of the material. So thanks to the University of Limerick and ATIP, we were provided this kind of data, and then we could create the digital twin with both production and simulated data. Next slide, please. So how is it inserted in Bio-Uptake projects? Mostly it can be reproduced on other production projects, so applicable to other industries. It is used in other tasks of the project, such as the decision support system for product design. And it also can be used as a standalone, I would say, with finished element method simulations or validation of part design and production feasibility. Next slide, please. So on the project, we can see on the left here graphs that were created thanks to characterization of done by the partners. So we have PVTs, we have tensile stress versus temperature or viscosity curves here. Thanks to this characterization, we were able to make some deformation estimation of the product. Also thermal analysis of the mold during the production that we can see, and most importantly, the filling pattern could be estimated and the part validated for production. Next slide, please. Also digital twin, and here with the DOE done in finished element analysis enables to find optimal parameters, and that can be used to start production trials, let's say. And we can say that we have some first parameters to start. So it is a way to make the launch of a tool faster once the tool is created. Next slide, please. Then we worked on the decision support system for product design, I guess. So what is the support system? We will see this. How is the decision support system created, or how was it created? And how is it relevant in the overall Bio-Uptake project? Next slide, please. So basically, it's a Python application with a web API as a user interface, and it is backed by deep learning and finished element method simulations. And it is created to help project manager for product design and new material use. So the screenshot that we can see here under is basically sliders with the process parameters, and we can see outputs of quality criteria that we entered. And so by changing filling time and so on, we can see in this case 3 dimensions and 1 weight that change accordingly. Next slide, please. So how was it created? Here we have the model definition and benchmark. So we started with different machine learning and deep learning or statistical modeling methods. So random forest, XGBoost, linear regression, and backpropagation neural network. We've done some benchmarks. We selected some backpropagation neural network as the more efficient one. So then we could step to the next step, which is on the next slide, please. So this way we created an experimental matrix that we produced parts out of, and we measured quality criteria manually. So we've done 500 injection cycles to have 500 parts with different settings. And what we've done is train the AI model on this. And then we see on the next slide that what we varied is the quantity of experimental data could be implemented to the simulated ones in order to have a model that is more fit to what's happening in the real life. And what we've seen that is that the sweet spot was around 20% of real life measurements enables a closer fitting of the predictive model. Thank you. Next slide, please. And how is it relevant in the overall Bio-Uptake project? So this method, this platform enables to test different geometries before touch-ups. Here in the project, we only changed parameters, but we know that it works with different materials. So if we do production with different material grades, it will work the same, and it can also work with geometry changes, such as ribs, thickness change, different production strategies. What it enables is a reduction in needs for mold trials, such as time and material, that will, well, we have less waste of. And most of all, it quickens the use of new materials. So once characterized with a few characterization methods, we can estimate the production of any material that we could have. And I think that's it for this task.
Thank you so much. Moving from product design to process, we now come out to our decision support system for process design to explain how AI models can be leveraged to improve processes, and I'm pleased to give the floor to our expert, Ines Perez. Thanks, Ines. Don't hear. Try. No. Sorry, Anne, we have a little issue about the sound.
Yes, I see that. I don't know if
we can move.
Online. Yeah, we can move
to the next one, but in this case, Davinia needs to share their screen to show us the a live demo.
Yeah, that's no problem. Yeah.
Okay, Davinia, can you continue and then come back to Ines?
Yes. You can hear me?
Yes.
Oh, we can. Yeah.
Okay.
But we need to share your. I need to share your screen. Can you screen? No. Can you share your screen?
No. We need to change the presentation.
Yeah. So I'm changing it now. You
okay.
should have access now. Yeah.
And now
right
you
now.
can see. Okay.
Thanks.
Thank you, Marcos. Hello, everyone. This application shows the full traceability of a product across its entire life. It goes from the design phase to the final results. The traceability is shown in a visual way. All the product processes are organized and easy to see. First, we design the flow in 2 levels. At the first level, we define the main processes stage. The stage gives the general context of the product. We can select one node of the library or a custom node for enter the names you need. Okay. At the second level, for example, monitoring in this case, we define the real execution steps. This is where the processes data is recorded. We can select, for example, in this case, monitoring, edit, and we, sorry, but this presentation, I can select the name. Sorry. Can we put the, okay. We can select the node, edit the file, and at this level, we registered files. These files can be local files or cloud files. Include ER results, quality results, and manufacturing results, generate or not during the process. In the case of Moses, for example, on monitoring, we select the repository file and image. And 64 MBNP, open. Okay, and the output file, select the repository file, an image, overlay 64, okay. Save the process and we can check. Oof. Photo and sorry. The same. We can have the two photographs, and we can say if the valid or not valid the process.
As Davinia shown, the upper is the process of images, and the low, sorry, the down was the input, and then all data is recorded about the data of if it's valid or not, as Davinia said, to
yes,
shown in the budget, no, in the budget in the upper corner of the blocks. Continue,
yes,
Davinia. Sorry.
The application allows us to easily see if a product or lot is valid or not. We can see how many times it's failed and if the process needs to be changed, if you need the material or something like that. Everything is recorded in a clear and visual way. There is also a short summary that helps with analysis and decisions. In summary, that the application helps us keep traceability of processes that work well and processes that did not work, including the reasons why and all information that the process data flow. This is all for my part.
Thank you so much, Davinia. Ines, are you ready? Ines, can you hear me? Can you hear us?
Okay. Yeah, so I think in this case, what we can do is we'll continue. We had the FAQ next. And what I could say, Ines, is what we can do later is to record the session with you, with Nicola, and we'll put that on the website. I think that will be the best way. Okay. Okay. Because,
okay, thank you.
Yeah, I had the same issue. I had to restart my computer this morning because of its, I don't know, somehow.
No, I'm getting used to the software of Teams more than this platform is for that. And then the little issues about the equipment, the sound and video, but is no. Thank you so much, Anne.
You're welcome. So no, so we'll move to the, let me just move my screen.